My name is Lena. I'm a software engineer at Enigma. And Enigma tries to make a decentralized application to use private data.
I'm sorry, could you for 1 second show the page again? I just take a quick picture.
Sure, sure.
I don't know.
Yeah, I plan to just, yeah. This will be here for several seconds, yeah. Okay, so first of all, if by any chance someone has done the preparation step before, great. I guess most of you haven't. That's okay also. The VM is quite big, so I'm not sure that if you start now, you'll be able to join us during the workshop, but it's completely fine. This is optional. You can just follow along and download the slides and do it afterwards if you want. It's okay? I can move on, or cool. Okay, so so what we're going to do today, I'll do an introduction to Enigma solution, and then we'll do a workshop in which we are going to learn how we can build a secret contract on Enigma and how we can interact with that. Please, if you have any questions, don't hesitate, raise your hand. If these questions are regarding things not working on your environment, let's take it offline, please. Okay, so we're starting with Enigma, and why is that important for you to know. As you might know, blockchain are private, which is great, blockchain are public, which means that all data is visible to everyone, which is great for some application, but there are some other applications that everyone can think of that require private data, as medical data or credit scores, or let's say an application like voting. So Enigma tries to solve this problem by enabling the use of decentralized application who use private data, meaning encrypted data. We are working hard towards our first release, which is going to be Discovery. This is will be a public permissionless network, economically incentivized, and also compatible with Ethereum. By compatible with Ethereum, I mean that in a sense you could outsource your private computation to Enigma while doing the other functionality on Ethereum. Okay, I think it will be most simple to understand our ecosystem through our stakeholders. We have developers who are the ones deploy secret contracts. We have the users who use this decentralized application developed by the developers. And we have the workers who are the ones that execute the computation, and they are getting paid for the execution. Okay, so developers, they are writing what we call secret contract, meaning it's like smart contract run on private data. They deploy it on the Enigma network. We have users who can interact with this secret contract, which are our execution units, and send computation jobs, which we call task. And the task also sends to Enigma network. We also use Ethereum for saving metadata of the task. And we have the workers who are the ones that are executing those tasks. Workers are selected for the task on a weighted lottery based on their staking. Okay, so some more key terms. Secret contract and task we have already defined. Let's talk about state. State is very much like storage on Ethereum. For stateful computation, we can save persistent data on Enigma network. Another key term, WebAssembly, or in shortcut, WASM. This is a standard for binary code, originally developed for web application, but also had in mind other environments like ours. So we use WebAssembly in a way that our code of the secret contract is compiled to WebAssembly, and it is what is being deployed on the network. GAS, also a term that will be that is used in our network. Again, this is very much familiar to Ethereum developers or users. Each computation job has a fee, and the fee is being calculated by defining two parameters. One is gas limit, and the second one is gas price. Okay, we'll move on to discussing about the development environment in what we're going to use in order to have a sense of Enigma network. Okay, so we have recently released a development network, which is a sandbox network of Enigma that you can run locally on your computer. And it will give you, it can make you familiarize with Enigma solution. It gives you a way to develop a secret contract, deploy them to the network, interact with them, and test them. Okay, so from now on, if you see this queue, it means you can jump in. I don't know if it's okay, it's optional, like I said at the beginning, but just have that in mind. Okay, so first of all, we're going to navigate to this path, which is the root path of the problem that we're going to solve. And first of all, we need to start our local network by running discovery start. You should see something like that. It means all the relevant components of Enigma are being initialized and ready, and are running and ready. From now on, for the next phases, we will use another tab because we need the network running to communicate with. Okay, so we're now moving on to the fun part, the workshop. The workshop is divided into two phases. On the first phase, we're going to develop our secret contract, and then we're going to interact with it. Okay, so secret contract on Enigma are written in Rust. Why Rust? It's memory safe, it has a good performance, it has great package manager, and there's a fantastic community. It has been voted the most loved programming language 3 years in a row. Developer? Yeah. Okay. So before we diving into the code, let's try to introduce the problem that we're going to solve. The problem is a millionaire problem. We have two guys, Alice and Bob. They are millionaires, and like any other millionaire, they're obsessed with both their wealth, but also with their privacy. So they're very interested who is the richer between them, but they want to find that out without revealing their exact wealth. So that's this is the problem that we're going to solve. we're going to develop a secret contract implementing this problem. And we're going to, and it will be, its interface will be adding a Millionaire data. Bob will add his data, then Alice will add her data, encrypted, of course, private, seen only to the person who make this request. And then we're going to call compute riches to find out who's the richest, which can be done by in either one of Alice or Bob, or by a third party. And of course, the compute riches will only give the address or the name of the millionaire without revealing the wealth. Okay, so this is the millionaire problem is the root directory which implements these problems. And now we're going to deep dive into the code implementing that. Okay, so we recommend to start the implementation of each secret contract by adding this annotation, the no STD annotation. Rust has a standard a library which provides a lot of useful functionality. But because we are running, we're using the WASM, the WebAssembly sandbox, not all functionality is being accessible to us. So, so even like if we use some of using some of this functionality like threads, it can it will compile, but we might have a runtime exception. Thus, our recommendation to remove the use of the standard library. But don't worry, there's useful functionality like strings and vector, which will be bringing into scope of the contract by adding, importing Enigma-specific libraries. So we're bringing into scope one of the Enigma libraries. It's called ENG-WASM. We imported, and then in the second line, we're bringing into scope everything within. So what it has is subset of the standard library functionality as described, but also Enigma-specific services like reading and writing to and from the state. What state? The persistent state, the storage that we've discussed before, which is also being kept encrypted. The next thing that we're bringing into scope is another Enigma library called ENG-WASM derive. And we're bringing into scope only one annotation from it called pub interface. And this is required because this is enable us to expose public function to be called from outside. And we'll see the use of it shortly. The last thing that we need to bring into scope is Serde, which is create or package in Rust, responsible on serialization and deserialization, and we'll see the use of it shortly. Okay, here we're defining a constant string millionaires, and we'll see the use of it very shortly. Okay, now we're going to define a struct that will represent a millionaire. And like we saw before, a millionaire will have two parameters. One is the address, the ID of the millionaire. The other thing is its net worth. Please note that above the definition of the struct, we use annotation, which what it does, it auto-generates code for serialization and deserialization, and it is required for us for reading and writing from state, which we'll see in a sec. I want to all you have pay attention to the types of the parameters. This is H256 and U256. there's a list of supported types that can be defined in the secret contract, but for publicly exposed types, and these two types are part of this list, and the full list can be found in the appendix of this presentation. Okay, now we're moving to the definition of public-facing function. So we're defining here a trait which is very similar to abstract interface for the ones of you who are familiar with Java. So we're defining here two functions. The name of the trait is not something that is fixed. We used here contract interface. You can use whatever you want. So we're defining here two functions, again, like we saw in the, previously on the example, add millionaire to add the information of a new millionaire, and compute riches to find out who is the richest from the current millionaires added. I would like us to pay attention for something important at this point. If we have a constructor, if our secret contract requires a constructor to doing some initialization, then the definition of the constructor should be added here. In our case, there is nothing that we need to initialize, thus we leave it empty, but a default constructor will be generated automatically for us. And the use of this constructor we will see shortly. Okay, so now we're starting with the definition of our contract. Again, here we define a struct named contract. This is also not a fixed name. You can use any name that you like. In Rust, in order to implement a trait, you have to define a struct which implements the traits in it. So this is the struct that we create. Here we are going to implement a private function to be used by our other functions, and the function is get millionaires. And what it returns a vector of millionaire. The millionaire is the struct that we've defined before. And here we are, please note that we're using a service brought to us in the ENG WASM package. It's called, it's read state, and basically what it does, it reads from the contract state, the persistent state. The state is a key value store. The key has to be a string. That's why we're using the const string we've defined at the beginning, as you might remember, and this const string is mapped to a vector of millionaires. What we're doing next, we're reading from this state, which returns us what we called an option in Rust. And then we're doing a match, using match. It's a match expression very similar to switch case from other languages. We can have two values. Or we have some value, in this case a vector, and then we return the vector. Or we have none, meaning no millionaire has added so far to the state. So we're initializing a new empty vector. And this is what we return. Okay, we're moving to the second part of implementing our function that we've defined in our trait. So the first function is add millionaire, which received two parameters of the newly added millionaire. And basically what we're going to do is to read from state, to append a new millionaire to the end of the vector, and to write to state. And this is what we see. Here you see the use of the private function that we've defined before, the get millionaire. It returns a vector of the millionaire. Then we push a new millionaire struct, which is created and with these two parameters given. And then we use another service, the corresponding service to read state, which is write state. And again, what write state require? is a key and a value. And this is the syntax that we've defined to write into state. The key has to be string. The value, again, the newly updated vector. Please note that you can write into state many such pairs separated by comma. But in this case, we only have one. OK, now we're moving, the previous function has gone up. Now we're moving to the second function, which is compute riches. And it returns the address or the name of the richest millionaire. What we're doing here is also, again, calling our private function, getMillionaires, to read from the state the current vector of our millionaires. And we iterate upon this, when defining a filter maxed by the net worth. So here also we are seeing, again, using the match expression. If we have received the millionaire, we return its address, only its address. But if we've received nothing, meaning the list is empty, we're returning an empty address to indicate there is no millionaire. OK, so we finished our Rust code. This is our first secret contract written in Rust. And now the next step will be to compile it. We can run discovery compile. And what will be created is a .wasm file, which will include the bytecode in WebAssembly. OK, the next step will be to deploy this contract into the Enigma network. The ones of you are familiar with Truffle, this is very similar. We use discovery migrate command to deploy our contract to Enigma. The environment comes already with two files. One is an initial migration file, but the second one called toDeployContract. And it comes already, if you open that, probably after this workshop, you can find implementation of a deploy secret contract function. So the function is already implemented there. You can look at the implementation. We're not going to go over it. We're going to see how we can use it in order to deploy a secret contract to the Enigma network. The deploy secret contract receives a configuration object. And here we are seeing the use of this function in order to deploy our millionaire problem contract. So what this function requires from its parameters, the file name, of course, the file name which includes the bytecode of the compiled contract, which is millionaireproblem.wasm, a function. Here we see the constructor that we've discussed. Again, very similar to Ethereum. Once a contract is deployed to the network, its constructor is being called. And constructor can be called only once on the deployment. Again, we have no arguments for our constructor. Thus, our arguments is empty. And we define here gas limit and gas price. Also, we're defining here an Ethereum account, the from, because this is also a computation task that needs to be paid for. But we'll touch that in more depth shortly. OK, after we've defined this configuration object, we simply using the deploy secret contract function with this parameter. OK, the code is already there. And we can go and run it and deploy our contract by running discovery migrate. OK, great. So now we're moving to the second part. After we've deployed the secret contract, now we see how we can interact with it. And for interacting with the secret contract, we'll be using Enigma Jas Library, which is a client-side library for interacting with secret contract. It enables you to send tasks encrypt task inputs, something that perhaps wasn't mentioned yet, too much, but everything, all the inputs are encrypted and the outputs are encrypted. So encrypting the user, the task inputs, submitting tasks to the Enigma network, and getting the computation result and the status. Okay, a partial API, which we'll see the use of it, is compute task, which receives the following parameters. Get task result function and get task status. We'll see the use of it in a sec. Okay, so as we've described already, we're going to do the following. Add Bob's information, then add Alice information, meaning calling a task with encrypted data on Bob, calling a task with encrypted data on Alice, and then calling a task, compute riches, and getting the result. So here we are, I want to look at 3 lines from the end. Enigma is an instance of the Enigma Jas library. You have to trust me, it was initialized outside of this slide. And we're going to call one of its methods, compute task, with the following parameters, which are defined above. We have the task function, which is the add millionaire, which is these 2 parameters, and we have the task arguments as follows. Again, they'll all be encrypted when sent to the network. I want to mention a small thing. You might see that the types are a bit different from the types that we've seen in Rust. They're equivalent types in Solidity. Again, in the appendix, you could see a mapping of all the Rust supported types to their equivalent Solidity types. Okay, now we're doing a naive. After we've run compute task command and sent the task to the network, now we want to discover how whether the task was finished. So we're doing a naive polling to get the task status, and once we see it finished, we can end. Please note, the add millionaire function doesn't return any output, so we can finish at that for this function. This is practically the same code with different parameters. Now we're doing the same add millionaire with Alice. Okay, and now we can call the compute richest. Again, this is very similar. We call the compute task with the following parameters. The task function is different. It doesn't have any arguments, but this is the same API. Again, we need to poll the network to understand when has the task was computed and finished. And only after the task has finished, we can query the network for the result. So we're going to use another API function, which is get task result. And this is an encrypted result, so we need to decrypt it. And c'est la vie. Now, all the code in the last slides are basically taken with small modification from the test. In the root path, under the test directory, you can add your own test for testing your secret contract. You have already in your environment a test for the millionaire problem, and the code that we've seen is from there with small adjustments. So by running discovery test, the test that is there will run, and you can see the result. But basically, the purpose of it is for you to use that when you're trying to test your develop contract. What else? We have already in the environment a client folder with a starting point for building a front-end the app. So you can use it as well already in your environment. Okay, so what we've done today. We've developed a secret contract, and we've interacted with one. Questions? Yes?
What's the encryption that you're using? Is it public-private key pairs, or how do you know how to decrypt the results? How do you know how to encrypt what you send to the contract? How do you know how to encrypt the contract when you publish it?
So it's a very good question. This is something that really wasn't covered on this presentation. What is happening is that once a user wants to send a task to the Enigma network, first it queries the network for the worker, okay? And after it has the worker information, it do a key exchange diffie-Hellman in order to both of them to have a symmetric key. And this is how it's done, basically.
Okay. And so the same symmetric key is used for publishing contracts, writing contracts, etc.
Yes.
So if it's using symmetric key, can the worker, so basically when you submit a task, he has to read the state, etc. He has the ability to decrypt the data, right? And if he has the ability to decrypt the data using the symmetric key, he is able to read the state of the secret contract?
It's a very good question. The state is decrypted in other keys, okay? What is happening is that we have what we call an epoch, or like we can think of it as a time interval. In this time interval, there's mapping, if we can use this word, for workers for different secret contracts. Meaning, at a certain epoch, only a certain worker can work on this secret contract. So before working on this secret contract, he has to have the keys for decrypting the state for this secret contract. So this is a different encryption, yeah. More questions?
The result from the computation is public. It's not encrypted, right? That gets decrypted by the contract from the Enigma network. So whatever is returned to the front end is public. It's not something that is encrypted.
No, the output is also decrypted. Encrypted, sorry. The inputs are encrypted, the output are encrypted, and the persistent state is encrypted. Everything is encrypted here. The only thing that is public is the code, the bytecode of the secret contract.
Okay. So does the encrypted data arrives to the client? For example, if I'm using a browser to interact with the network, the data comes to the client, to the browser, encrypted?
Yes.
And I decrypt it because I have the keys.
Exactly, because the user is the one doing the key exchange at the beginning of the task with the worker.
Oh, very good.
Yes.
Or you could return the results to Ethereum. You could return public data through an Ethereum callback.
Okay. Yeah. So something that we haven't touched upon, but we have an Ethereum bridge, meaning that we can call Ethereum contracts after the execution of task on the Enigma network. Thank you for bringing this up. Yes?
So can anyone join the network as a worker? And if so, he will be able to have access to the keys that are displayed for each epoch, right? So can someone join the network as a worker and just listen for the keys, and when he has access to them, he can read the state of the contract?
It's a great question. You're raising another thing that wasn't covered on this. But what the Enigma network is the worker, like all this works with using trusted execution environment. Okay, so all the code all the computation are done via the enclave, which is an isolated environment within the worker's machine. So let's say you want to be a worker. First of all, you have to stake some values, but you have to have a trusted execution environment, and what is run there is isolated. So more good questions? Thank you. Yeah. So if you want to follow this workshop or to learn more, you can do it afterwards. Unfortunately, it was hard to do it during the workshop itself. Any more questions? Yeah.
Is Enigma Ethereum only service? Can I couple it with other blockchains?
At this phase, we are compatible with Ethereum, but we might consider.
You'll become agnostic eventually.
Sorry?
You'll become agnostic.
Exactly. Basically, yeah. Basically, we're agnostic, but our first release is very combined with Ethereum.